Hello, today we'll talk about change of variable and how cylindrical and spherical coordinates are related to it. In fact, cylindrical and spherical coordinates are two ways of how to change a variable. Let's get started. I'm going to use the most general case, change a variable. Let's say we have some function, f. I'll do it in 3 dimensions so we can relate better to spherical and cylindrical coordinates, x, y, z. This is our function. So we want to transform each variable into something. So let's say that x is a function of u v w. Same thing happens for y. Y is a function of u v w, and z is a function of u v w. So what this could be, so for example, let's change it to cylindrical coordinates. So in cylindrical coordinates, our x would be u cosine v. So if you actually use proper cylindrical coordinates, u would be rho and v would be theta or phi, whatever is used in there. Y would be u sine phi, and z would equal to w. This is basically spherical coordinates. I'm just using slightly different variables. I meant to say cylindrical. But anyway, the basic rule is if you want to find a volume of a function, take a triple integral of f x y z, and then dx dy dz, but I'll just write dv, equals triple integral of f of g of u v w. And basically it's going to be f of g, and g is a function, it's a vector of x, y, z, and each vector stands for this corresponding variable, u cosine v, u sine v, and w, so on. Times a determinant, so times a determinant, absolute value I guess as well, of g, dg. I'll just write like that. Determinant of dg. And once again I'll write dv prime, or dv1 I guess, and this basically means du, dv, dw. So basically, whenever you're trying to take integral and you transform cylindrical or spherical coordinates, you just take function, plot u, v, w in each x, y, z as like given by this function, and then you have to multiply by something. And this something is basically determinant of derivative of g. So this is our cylindrical and spherical coordinates in terms of u, v, w. Okay, to get a determinant of d g u v w, let's value this. You basically have to take a derivative of each function with respect to u, like its variable. So basically what I mean is we take x with respect to u v w, then y with respect to u v w, and z with respect to u v w. So we're gonna have basically 3 rows and 3 columns. So x with respect to u is just gonna be cos v. So cos sine v. X with respect to v is gonna be u negative sine v. And x with respect to w, this is going to be 0. This is just our x derivative. Now let's take y. Y with respect to u would be sine v. Y with respect to v is going to be u cos v. and y with respect to w is going to be 0. And finally, z with respect to u is 0, z with respect to y is 0, and z with respect to w is 1. The way I like to determine it is just to pick a row and keep going from left to right. But 0 times anything is 0, plus 0 times anything, once again, is going to be 0, and 1 times cosine v times u cosine v. So this is going to be equals to u cosine v squared, plus, actually minus, negative u sine v squared. Okay. So as you can see, we can just factor out u, negative signs cancel, and all we get is u times sine plus cosine squared, which is 1, means this whole thing just equals to u. So if you remember, if you do cylindrical coordinates, you have to multiply after a function times r, dr, d theta, dz, right? And in our case, we basically have u instead of r. It stands instead of radius here. If you take determinant of spherical coordinates, what you're gonna end up having is u, in this case, u square sine v. Typically, how you actually see it is r squared sine theta or sine c. Depends whichever version of spherical coordinates you use. Now I want to finish up this example with sphere. So let's take the sphere that equals to 1. X squared plus y squared plus z squared equals to 1. There's a couple ways to actually do the integral of a sphere. First typical way, let's use spherical coordinates. So this would be integral between 0 to 2 pi, then integral between 0 to pi, and integral between 0 to 1 of r squared sine theta dr d theta d phi d theta d phi. So basically what we have, phi is your longitude, goes around the circle. That basically has 360 degrees, which is 2 pi. While theta is your latitude, where you basically go from top to bottom. And this is only 180 degrees between 0 and pi. And you have radius of 1. Therefore, radius goes between 0 and 1. Okay, this is how you do it in spherical coordinates. Now, I want to convert it into cylindrical coordinates. So, basically, what we want to calculate is z. So, our z is going to equals to 1 minus x squared minus y squared, and this whole thing is square rooted. This is how our z is going to look like. Okay, so for cylindrical coordinates, basically what are we going to have is this circle is your polar part, so x and y, I guess, or r and theta, and then we have z, and z is going to equals to that. And as you can see, it's going to be minus, in parentheses, x squared plus y squared, which is basically r squared. So you can rewrite this whole thing as square root of 1 minus r squared. So now let's do our integral. So our integral, once again, going to go between 0 to 2 pi. This is our circle here now.